In this video, we will be presenting our work for BlockFL Plus, a blockchain-enabled scalable decentralized federated learning with Chardings. We will first run through the introduction and motivation of this project, then the system design and overview before demonstrating the prototype user interface. First, let us begin with a quick overview of the original framework which our framework improves upon. The original framework is Blockchain-Enabled Federated Edge Learning, or BFEL for short. It consists of an application layer and a blockchain layer. First, each task publisher broadcasts a learning task to edge devices with relevant data in the application layer. Edge devices then train the given model and generate local model updates. Qualified model updates are compressed and stored in a training subchain. A trading subchain also allows the model's owner to trade their final models with other parties. All the subchains are anchored to the main chain for effective governance. Overall, BFEL facilitates federated learning model training on edge devices without exposing its data to the network, thus enhancing security and decentralization. A deep gradient compression scheme is also adopted to reduce communication overhead, coupled with the multi-blockchain framework have empowered scalability. The BFEL model faces the numerous transactions sent from the training and trading subchains to the main chain, which imposes a bottleneck in the transaction throughput on the main chain. BFEL model uses consortium blockchain to build the subchains and main chain. A consortium blockchain is a permissioned blockchain consisting of verified nodes that do not fully trust each other. Therefore, a fault-tolerant protocol is needed, such as the regular fault-tolerant, RAFT, to ensure consistency in a network by using two F+1 nodes to allow F nodes to crash down. However, in many blockchain systems, the number of participating nodes is much more than 2F+1. In such systems, establishing consensus by cross-verifying with all other nodes in the network degrades performance and impedes the model from scaling. Therefore, we introduce a Charding technique that partitions nodes in the main chain into smaller clusters of the size at least 2F+1 to process multiple transactions in parallel, thus improving scalability. Next, we will be looking into the FiscoBCOS architecture that we build the framework on. FiscoBCOS is the first safe and controllable enterprise-level financial consortium blockchain platform open source by domestic enterprises. It has three layers: console, Java SDK and FiscoBCOS layer. The console layer allows users to perform any requests to the FiscoBCOS blockchain, including querying information of the chain such as block number, deploying smart contracts and calling smart contracts functions, managing ledgers or groups of ledgers. The Java SDK layer helps the console layer establish a connection with the blockchain node to request access for blockchain node data. The FiscoBCOS layer is where FiscoBCOS blockchain nodes reside. To implement Charding, we need to implement it across three layers. However, the primary technique lies in the FiscoBCOS layer. To see how Charding can be implemented in the FiscoBCOS layer, let us look at the consensus protocol that FiscoBCOS runs. FiscoBCOS supports practical Byzantine fault tolerance, PBFT, and replication in fault-tolerant, RAFT, consensus algorithms. In this framework, we focus on the RAFT consensus algorithm. There are three types of nodes in the RAFT protocol: follower, candidate, and leader nodes. All our nodes start in the follower state. The follower node becomes the candidate node after a timeout and starts a leader election. Each follower has a different timeout to ensure there is only one follower node becomes candidate node. The candidate node requests for votes from other nodes, and it becomes the leader node if it receives the majority of votes. All the changes in the system now go through the leader. Each change is added as an entry in the node's log. This log entry is currently uncommitted, so it won't update the node's value. To commit the entry, the node first replicates it to the follower nodes. Then the leader waits until a majority of nodes have written the entry. The entry is now committed on the leader node, and the node state is 5. The leader then notifies the followers that the entry is committed. The cluster has now come to consensus about the system state. Now let's see how sharding is implemented. Nodes are partitioned into 2 clusters. Each cluster runs its own election process. Now let's add another client. Each client sends requests to each leader node. Leader node then broadcasts messages to other nodes in its cluster. After establishing the consensus with other nodes, leader node responds to the client. Now let's heal the network partitioning. Which leader with higher election term, aka is elected first in the entire network, will be the final leader. Other nodes are synchronized to ensure data consistency. Now, we will demonstrate the BlockFL framework. First, we build a fiscal BCOS chain consisting of 5 nodes by running the following command. We now see a folder of 5 nodes. In each node's folder, we can find the node's information, such as the port assigned to or the consensus information in the group it belongs to. Note that this configuration file can only be changed before the nodes launch. After that, it does not take effect. We will change the group's consensus to Raft instead of PBFT by default. We also add another section for sharding. Here, we partition the group into 2 shards, shard 0 and 1. Shard 0 consists of nodes 0, 1 and 2. Shard 1 consists of nodes 3 and 4. We copy this configuration and paste it to all other nodes. We then can access the console. However, before that, we must copy the SDK files from the nodes to put them in the console folder. We also configure the console's config file to enable sharding. We add other peers in a section for sharding. Note that this partitioning must be consistent with the one we did in the consensus configuration file. All is ready. We now launch the nodes in the console. Firstly, we check the current block number, which is 0. We now execute the primary function. We enable the framework to take multiple commands to run at one time. We will demonstrate by deploying 2 simple smart contracts, Hello World and Crypto, and here is the result. Now, let's recheck the block number. The block number is now updated to 2, which means that 2 transactions are written successfully into the chain. With that, we have come to the end of this video demonstration. Thank you for listening.